review inverse functions and log functions. So we're back in chapter 1. We're not doing any calculus today, just talking about functions. So that next class we can take derivatives of the log function and other inverse functions. Okay, so we're going to start with a find the inverse of this function question. So does anybody remember the sort of general approach and how to find an inverse function? Yeah, you swap the x and y and then solve for the y, or solve for the x and then swap the names. Yeah. So my usual process, I start by writing y equals. I make all the y's x's and x's y's, so this becomes x equals. And then I want to solve for y, get y by itself. And when you have solved for y, you get the inverse function. All right, so what should I do next here if I want to solve for y? Sure. So I have xy plus x equals y. If I want to solve for y, I should probably get all the y's on the same side of the equation. Okay, so I'm going to have xy minus y, and then I'm going to move the non-y term to the other side, equals negative x. This is the original function. Sorry, it's multiple choice. Those are the options for the answer. Yep. Everybody with me so far? Just trying to get y by itself. So started by multiplying both sides by y plus 1. So I distributed my x to my y plus 1, and I got xy plus x. I was left with a y on the other side. And then if my goal is to get y by itself, I should put all my y terms on one side and all my non-y terms on the other. All right, how am I going to try to isolate this y here? I've got an xy minus y. What do you think? Yeah, I don't think that's going to be helpful because I want all my y's on one side, right? I'm trying to get y by itself. Like, what if that said 5y minus y? What would you do? Before you can divide. Yeah, you'd combine like terms. In this case, it looks like factoring. There's a y in both terms here, so I'm going to factor it out. I'm left with x minus 1. Then what do? I've got something times y equals something else. How do you isolate the y? Divide both sides by x minus 1.
That's still part of problem A, or is this something different?
Yes. This is multiple choice. A, B, C, D, and E are the possible answers.
Oh.
My original problem is f of x is x over x plus 1. I'm just trying to find the inverse function. All right, so my x minus 1's cancel here. And I'm left with y equals x over x minus 1. The x on top had a negative sign, yeah. Okay, there we go. Which of my options, A, B, C, D, or E, matches what I just found? How does B look like negative x over x minus 1? This is the inverse. This is my answer. One of these has to be equivalent to that. D? A? Not, okay, good. That's a good start. None of them look exactly alike, right? Okay, so what's different? I've got a negative x on top. None of my options have negative x on the top, right? I have two options where there's an x on the top, right? Right, so it's got to be C or D. There's no way it's an x plus 1 or an x minus 1 on top, because my function has a negative x on top. All right, how could I move that negative sign? How could I deal with that negative sign so it's not on top? You can just move it to the bottom. Yeah, when you have a negative in a fraction, you can put it on the top or the bottom or out front, all equivalent, right? Like if I wrote negative 1/3, that's the same thing as 1 over negative 3 or negative 1/3. All the same, right? So that's what I'm going to do. I'm going to rewrite this where I put my negative on the bottom. Okay. What happens when I distribute that negative? It becomes negative x plus 1, which is the same thing as 1 minus x. And that is C. Mm-hmm. Yep. So in general, that's how you find inverse functions. Swap x and y, solve for the new y. All right, do you know what these things mean? Y equals log base b of x? Yes, yes. So logarithms are exponents. Okay, so log functions are the inverse of exponential functions. So you can always rewrite a sentence, a mathematical equation that has a log in it, as an exponential mathematical equation. Just like you can always rewrite division as a multiplication, right? I could say dividing by 5 is the same thing as multiplying by 1/5. So you can always rewrite a log as an exponential. And your base is always that little number that's low. So that kind of reminds me that it's the base because it's low. B. And then your exponent and your result switch places. Because that's what inverse functions do. They swap x and y, right? So now this is b to the y equals x. How about this one? What if I just write y equals log x? How does that translate? Yeah, that one's a 10. When there's no base written, you assume it's a 10. So that says 10 to the y equals x. And what about ln, or the natural log? Y equals ln x. Yeah, your base is e when you see the ln. So that says e to the y equals x. And also, I know you guys use Mathematica and Wolfram Alpha for a lot of things like in physics. So I just want to give you a little warning that when Mathematica uses the word log, when they write log, everyone in the world thinks base 10, but Mathematica thinks base e. So they don't use ln, they use log for the natural logarithm. I don't know why, but oh, I think you have to like explicitly say base 10. I don't remember how, but yeah. All right, so if I have the log of 800, I want to figure out an approximate answer, no touching your calculator allowed. Trying to figure out the log of 800. So the log of 800 has to equal something. So let me write that. Log of 800 equals something, right? So translate this to an exponential equation. Nope. 10 to the y. Yep, the base is always the little index numbers, which is not written in this case, so it's a 10. 10 to the y equals 800. So I got to try to guess a y. What could I raise 10 to? Be very approximate if you have to get 800. 10 to the 100? That's way bigger than 800. Yeah. Between 2 and 3, yeah, because 10 squared would be just 100, but 10 cubed would be 1,000. Probably closer to 3 than to 2, yeah. So between 2 and 3, closer to 3. That's my guess without having to use a calculator at all. All right, so then I'm going to use my calculator just to verify. Okay, so you've got a log button, so I'm just going to hit log 800. and I get about 2.9. Log of 800 is approximately 2.9. Okay. And then I also asked for an equivalent exponential equation, right, that relates the 2.9 and the 10 and the 800. So what would my equivalent exponential be? Yes, 10 to the 2.9 should be approximately 800. And then we can just check that. 10 to the 2.9 gives me pretty close to 800. Why didn't I get 800? Because I rounded. There's a lot more decimal places, yeah. If I hit log of 800, log 800, and then I did 10 to that answer, it should give me the 800 back because it's going to keep all those decimals. Second answer, it's right next to the enter button. Yep. Yeah, it's helpful. All right. What's the relationship between e to the x and ln x? They're inverses, yeah. Inverses, which means they undo each other. Okay, just like multiplication and division undo each other, right? Exponential e to the x and the natural log ln x undo each other. What's the relationship between the graphs of two functions that are inverses? They're mirrors over the line y equals x, which kind of looks like a 90-degree flip, but it's not really the same thing. Okay, so they are mirrored over the line y equals x. Right. Yeah, it's a slope of 1, y-intercept of 0. Yeah. Okay, so I'm going to sketch e to the x and ln x on the same set of axes using this mirror property. So I'll start by doing e to the x. X, e to the x. And then I'll do x, ln x. Okay, so when x is 0, what is e to the x? 1. Yep. Yep. And then when x is 1, 2.7, or e, right? E to the first is e. 2, 7.4. Okay. That's good enough to start because we know the general shape. So I've got 0, 1, 1, 2.7-ish, 2, 7.4-ish. And I know that that is generally increasing. And this has an asymptote at 0. Okay. And then if I graph ln x, inverse functions just swap the role of x and y. So my table of values is going to just take each point on e to the x and switch the coordinates. So we'll have 1, 0, 2.71, 7.4, 2. And that should be good enough to start. And then I'm just going to make sure that I mirror over the line y equals x. So I've got 1, 0, 2.7, 1, 7.4, 2. I'm going to sketch in the line y equals x so that I can visualize the mirror effect here. Okay, so imagine the purple graph of e to the x being reflected over that green line. You can see the 3 points that I put on earlier would reflect onto the orange points. And then if you continue, it looks something like this. So that would be the graph of y equals ln x. Yes, you can't take the ln of 0. Good. Yeah. Because that means that e to the something would have to be able to give you 0, right? And there's an asymptote there. Okay, so there are 5 basic properties of logarithms that can be useful when you're trying to manipulate something, doing some algebra, solving an equation, or taking a derivative, right? It can be really helpful to have these 5 properties. So if you want to take the log of a product, that breaks into the log of A plus the log of B. And that feels weird, but when you think about that logarithms are exponentials, right? Think about like if I wanted to multiply like bases, if I had x to the A times x to the B, what do you do with those exponents? You add them. You get x to the A plus B, right? That is the equivalent property when you write things in terms of logs instead of exponentials. So you end up adding them instead of multiplying. Okay. And then a similar property exists where you take the log of A over B, log of A minus log of B. This one is particularly helpful in terms of solving equations that involve logs or that involve exponentials. If you want to take the log of A to a power, you can just pop that power off and put it down in front. So it becomes multiplication instead of an exponent. And then these last two are just the fact that e to the x and ln x are inverses. They undo each other. So if you take the ln of e to the x, you just get the x by itself. They just undo each other. They give you the x back. And e to the ln x just gives you the x back. And there is no nice property for the log of a plus b. So if you get somewhere and you have the log of a plus b, there's just nothing else you can do. Can't change it to log a plus log b. Okay, so we're now in a position to be able to solve exponential equations where we might have to use a logarithm in our solving. So I want to solve 200 is equal to 100 times 1.01 to the 12t. So first, I would like to isolate my exponential, right? So I want to get the thing raised to a power by itself first. So what should I do? Divide each side by 100. So my left side becomes 2, and I have 1.01 to the 12t. All right, when you have a variable in an exponent, this is where logarithms come in handy. I can take the log of both sides, and I can use any base log that I want. I could do log base 10, I could do log base e, I could do log base 17, right? You tend to use base 10 and base e because you have buttons on your calculator for those. And I use base e because you only have to write 2 letters. It doesn't really matter. So I'm going to write the ln of 2 equals the ln of 1.01 to the 12t. As long as you do the same thing to both sides, this is totally allowed. Just take the log of both sides. All right, and then the reason that that's helpful is because of this third property, right? Now I'm taking the log of something to a power. So I'm allowed to take that power off of the exponent and put it down in front of the log. So I'm allowed to just take this 12t that's in the exponent, pop it down in front of the log. So this becomes ln 2 equals 12 times the ln of 1.01. 12t, yes, thank you. Yes, yep. We can do a little justification of why they're equal and as soon as we finish this, if you want. All right, so how do I get the t by itself now? Yeah, I'm going to divide both sides by 12 and by the ln of 1.01. Right? And that will, then my 12s will cancel and my ln's will cancel, and I'll just have the t. So this side also divide by 12 and the ln of 1.01. So t is exactly equal to the ln of 2 divided by 12 ln 1.01. And then I could get an approximate answer depending on how the question was asked and who asked the question. If you're a mathematician for hire and you were asked to solve this problem for, you know, a bank that asked how long until this investment becomes $200, right? If you told them the ln of 2 over 12 times the ln of 1.01, they would probably never hire you again, right? Give them an approximate answer. But if you're working with other mathematicians, they tend to like exact answers. So I get about 0.606. Oh, look at that. Sorry. Here's another handy graphing calculator trick. If you press second, enter, the thing you just typed comes back up. And then you can just edit it. About 5.8. Okay, so that's it for the demo, but I do want to show you, yes. Are you sure? Okay. All right, so let's look at